Today we are going to look at the Neural Tangent Kernel, or NTK. The NTK can help us understand the training of the neural network under gradient descent. It says that the update of the model lives in a subspace that is defined by the kernel matrix. Interestingly, neural network is a truly nonlinear model in this entire series. So for all the models we covered so far, such as the span method, the local regression, and the SVM, they are secretly linear models defined in the feature space. So for the span method, we are secretly doing the linear regression in the feature space. For local regression, the linear model lives in a small neighborhood. And for the SVM classifier, we are fitting a linear classifier in the feature space. So neural network is actually the first true nonlinear model in this entire series. But here is the interesting part. In order to understand the neural network through NTK, we have to linearize the model around its initialization point. So that is something we're going to look at today. Okay, so let's get started. So in the last video, we have looked at how the NTK arises from gradient descent. So the update of the function value during the gradient descent is living in the subspace defined by the neural tangent kernel K. So see here that the NTK here actually depend on the gradient descent step of T. It means that in each gradient descent step, we will be having a different kernel matrix K. But for the problem when the NTK model works the best, we're going to look at a case where the K matrix is a constant. So that means K of T equals to K, right? So when this stays as a constant, then that means the update stays in the span of this of a linear subspace defined by the matrix K here. So that is obtained when the neural network is very wide, that has lots of neurons in it, is when we can kind of approximate the network with a constant NTK matrix K. Okay, so here is a problem we are looking at. It is a two-layer neural network. So we start with the input X. Then for the first layer, we have M in total of M neurons, right? So this gave us the weight from W1 to Wn, right? Then we take the dot product between the W and the X, and then we pass through a nonlinear function sigma. Then we multiply that by a vector A to get the output, right? So the last output is f of x. So that is the problem setup we're going to be looking at. Then I should specify the dimension of the problem, where the x, the input, is our vectors in d-dimensional space. And then we also have this regression setup where the label yi are real numbers. Then for each neuron, we'll have the wi vector, the weight vector, also being the d dimension. So in total, we'll have m neurons in the first layer. That means our total number of parameters here, theta, is given by we just combine all the weights together. That has the dimension of m times d. Also in here, we want to make one simplification to say that ai equals to 1. So that means we just sum over the result over each neuron, after the first layer, right? So that's a simplification we're going to make in here. And for neural network, the typical setting is that we want to randomly initialize the weight, so we can sample the wi from a standard Gaussian distribution. So I should say this is initialization. But one problem here is that if we initialize the weight in this way, the scale of the fx may not matches with the scale of y. Okay, so that is the issue. So we actually want to set this c here, to be in the order of 1 over square root of n, right? So that is something we're going to show with algebra later on. So the result of this factor here is that our neural network will stay very close to the initialization point. That the weight that doesn't change much during the training. So this is kind of the intuition why we can kind of approximate the training gradient descent training with a fixed kernel matrix. So that's something we're going to show in this video. Okay, so in order to see how this square root of m arises, we're going to make a few more assumptions about the data such that we want to normalize the data first, right? So that's a common practice for neural network as well. So here we're just going to say that the variance of y equals to 1. And then we also want that the norm of x also equals to 1, right? So that's a way to normalize the data. Okay, so now we are ready, right? So the goal here is that we actually want the fx and the y in the same scale, right? So that means we can say that the variance of fx equals to 1, right? So that is the goal here. So that the f and y will be in the same scale. Okay, so let's just do that. So we'll have variance of c times. So AI become 1 now, right? We make this simplification. Then we have the sigma. So that equals to c square times and then you'll see here because each neuron are independent, right, during the initialization, so we can actually um, write it out as c square and then sum, then variance of sigma. Okay, so now for this formula in here, we actually have a nonlinear function inside the variance. But we'll see here that we're going to assume that this nonlinear transformation is not going to change the order of the variance. So, so what I'm saying here is that we can assume that the variance of sigma t, right, equals to some constant. Let's call this constant alpha here times the variance of t. Right, so that is the assumption we're going to make, and it's actually a very reasonable assumption, right? Most of the nonlinear functions we use can satisfy this property. Okay, so this equals to c squared times the sum, and then alpha times variance of wi transpose x, right? So this variance term here, so actually this thing here equals to the expected value of wi transpose. I mean actually reverse the order of them. So we'll have x transpose wi transpose x. Okay, so this equals to x transpose, and then we'll have the variance of wi, then x, right? So that's actually equals to, and then we can actually replace this with identity, right? With identity, so it's just going to be x, the norm of the x, and that equals to 1 based on our assumption. Okay, so after this, right, we can just get rid of this term completely, right? That equals to 1. So what we have in the end is that we'll have c squared times alpha times m equals to 1, right? Okay, so here we only care about the order of the problem. That means we can just ignore the alpha here, right? That's going to be a constant, right? So it means that the c here is in the same order of 1 over square root of m, right? So that is exactly where we are anticipating. Okay, now the goal here is that we can actually plug in this the gradient for this function f into the NTK formula to see what happens. Okay, then for the next part of the video, the goal here is to show that the kernel matrix K stays constant during the gradient descent training, right? We want to show that the K at the T step of the gradient descent equals to K. In order to do that, we have two steps. The first step is that we want to show that at initialization, it equals to K as m goes to infinity. So this K here is kind of like an asymptotic limit case for the kernel matrix for the NTK. Then the second step is that we want to show the update. For each update, the t plus one step, the kernel kind of stays the same. So these are the two things we're going to show. Okay, now let's see how we can show this result. So the first thing we can do is just to compute the gradient. We're going to use that. Let me first compute the gradient with respect to one layer weight, Wi. Right? Remember that theta actually has all the gradient weights, all the layers stacked together, right? It's going to be W1 all the way to Wn, right? Has all the weight, but let's just do one layer. So that will equals to, you just apply the chain rule in here, then it's going to be 1 over square root of m. Okay, so let's just do the one layer first. So we apply the chain rule, and then we'll have 1 over square root of m times the sigma prime, the derivative of the nonlinear function. Okay, then for the gradient vector with respect to theta, we're just gonna stack everything together, right? So that will be the partial with the first layer to partial to the last layer. Sorry, the last neuron, right? They're in the same layer. Uh, okay. So what we can also do here is to compute the norm for this gradient vector, right? So that's also gonna come up. So the norm, and then let's just square it for the simplicity here, right? It's just gonna be the sum of the norm for each layer, for each neuron, right? So that equals to, and then m over 1, then sigma prime to square this one. Okay, so see, interesting here is that we kind of uh, have the setup for the law of large number, right? Because this, if you think about this as a random variable in here, then we take in the mean of this, right? So it means that it's gonna converge, right? I should say that this will, so I should say that this will converge as m goes to infinity by law of large number, converges to expected value of sigma prime wi transpose x square times the norm of x, right? We assume this to be 1. There should be a square in here. That doesn't matter. And then for this term in here, it's actually very similar to the equation we've seen above, right? Where we kind of remove this nonlinear function by assuming that there is a constant, right? It's approximated the variance as whatever term inside the nonlinear function, right? So you can say this is approximately some constant, right? Some constant alpha times the expected value of Wi transpose x square, right? So that's this term is just going to be the variance for the for Wi transpose x, right? So we've shown that this also equals to 1, right? But the important thing here is that we want want the order of this norm here to be all 1, right? Where we can just ignore this alpha because that's a constant. Okay, so the next thing that we can compute is a NTK, right? So that will be just the dot product between two data points, right? So we have this f x theta and then dot it with fx tilde theta. So that's the dot product we want to compute. So let's just plug in the expression here. Okay, so this inner product will just give us the we just need to sum all the neurons, and then we take the inner product for each neuron, right? So for each neuron, we'll have let's just write it in this way first. Wi, this is x, and then x tilde wi, right? And then we can just expand this term as summation, then square root of m. We will have sigma prime x transpose this inner product, right? And then we also remove another square root of m out. That gave us 1 over m with sigma prime wi transpose x tilde, right? Then you'll see that this sigma prime here is a scalar, right? That means we can pull it out. So we can write it in this way, 1 over m, and then sum, and then we'll have the sigma prime and then the inner product between x and x tilde, right? Okay, so see here, right? Once again, we have the law of large numbers set up. So let me write it in this way that when m is very large, goes to infinity, and then we also want the initialization, right? We want wi equals to wi initial, right? Wi 0. Then we'll have an expectation. So we'll have the expectation wi distributed as a standard normal. And then we can just copy whatever inside, right? So sigma prime will transpose x tilde, the inner product between x and x tilde, right? So that is the convergence behavior for our initialization when the number of neurons are very large, right? So that's very interesting. This is exactly how we're going to define the K matrix, right? So this we're just going to define this as K, and then it means that at our initialization, right, the K0 matrix will converge to K as m goes to infinity, right? Okay, so this concludes for our step one in here. Then for the step two, we're just going to show that the kernel matrix doesn't change much during the gradient descent steps. Where the goal is that we want to show the kernel at t plus 1 is approximately the same as the kernel at the step t. Okay, so now let's in order to show this, we can just subtract the difference between the two matrices, right? So actually, let's just use a pair of data points, right? So x and x tilde minus the kernel at step t between x and x tilde. Okay, so that's just gonna give us the dot product between the gradient vector and for the other data point, this is t plus 1. The key here is that the theta is t plus 1, right? Theta is t plus 1 minus the dot product between the step t x tilde theta t. Right, so here I'm just going to change the notation a little bit to make our life easier. So let's just call this thing gx, and then this is the gx tilde. And then we're just going to parameterize this with a difference, right? Let's just call this gx plus delta gx, right? So using the difference, then the other one will be gx tilde plus delta gx tilde. Okay, so now we can just keep expanding this dot product, and then what we're gonna left, right? What we have in the end will just be gx transpose times delta gx tilde plus gx tilde times delta gx. This transpose plus delta gx transpose delta gx tilde, right? Okay, so the thing here that if we want to show this difference is very small, all we need to show is that the delta g of x, the norm of this, right, goes to zero as m goes to infinity, right? So that's all we need to show. This become our goal. So this will imply that the difference, uh, the difference between the kernel matrix goes to zero, right? Okay, so in order to show this, let's just expand the terms. So the difference between the gradient vector, let's just square it. So that's gonna give us so we'll have the sum over all the neurons, and then we'll have the square root of m, and then transpose at t plus 1 step times x, and then that's going to multiply by x, and then we'll subtract that with the same thing but at the step t, right, times x, and then we multiply that by x again. Right, I think here it should be transpose, right? Okay, yeah, because okay, and then we're gonna square this entire thing, right? Or actually, we should take the norm of that. Yeah, we should take the norm of this. Okay, so actually, we should also square this 1 over square root of m, right? So that give us 1 over m. Okay, so let's just simplify this expression a little bit. So we have m 1 over m summation, and then so it means that this is smaller or equal to uh, we can just square this sigma minus at step p plus 1, step t, x, we square this times the norm of x, right? So that goes to 1, right? We assume this to be 1. Okay. Okay, now what can we do with this expression in here, right? So here we're gonna make one assumption about the function sigma prime. So we're gonna assume that the sigma prime to be L Lipschitz continuous. So that's actually a very reasonable assumption. I'll get into that in a second. So sigma prime to be L Lipschitz. So this just means that the sigma prime of A minus sigma prime of B is smaller or equal than L times the difference between A and B, right? So that is the Lipschitz continuity. And then we can just assume that to be true for the derivative of the function sigma. And then we'll just have this is smaller equals to 1 over m, and then times L, and then we'll have the sum 1 to n, and then the difference between the parameters, right? Between Wi transpose x minus Wi transpose, there's a t plus 1 at step t, right? The difference between those two. And you see here, this is just going to be the norm of the theta. Okay, so let me just write it down, and we'll have this, right? Theta t plus 1 minus theta at step t. Okay, now we're getting very close, right? So the last thing we need to show is that actually this theta here has the order of 1, right? So this is O1. And here we're just gonna see that directly from the gradient descent formula, right? So the gradient descent tells us the difference between the two parameters equals to the learning rate times the gradient, right? Times the gradient theta f x theta at step t, right? So when we take the norm of this, and then we take the norm of this, that's gonna see y, right? Because we already shown that this gradient here, the norm is O1, right? So when we multiply that by the learning rate eta, that's usually smaller than 1, right? So this whole thing here is just gonna be the order 1 using this formula. Okay, so all of this is saying that we can replace this term with some constant. So it also means that the square of the norm has the order of 1 over m, right? So that's going to converge to 0 as m goes to infinity. Okay, so the conclusion here is that once we know the difference between the gradient vector is very small, that's when we know the difference between the kernel matrix is very small, right? They're approximately the same after each gradient update. Okay, so we have done lots of algebra in this video, but let's not lose focus on the big picture. But the big picture is that the gradient descent gives rise to the NTK formula that we can approximate the training dynamics using this equation here, that the update can be described by the kernel function times the residual, right? But a key limitation for this framework is that this K matrix depends on the training step T. This video, all of our algebra is just to show that we can approximate this kernel with a fixed kernel matrix K here, right at the initialization. So I should say this equals to the K of 0. Right, this happens when the network width, so width m goes to infinity, right? That means we have lots of neurons. Then we can have this approximation. So all of this is saying that there is an implicit feature map for our neural network where the training behaves like a linear regression model in that feature space. And finally, just for a little preview of the next video, we can actually write this equation into a differential equation as this, right? We can move this eta term to the other side, and that can give us an ODE. So it means it's saying that the derivative of this f of x equals to the kernel times y minus f of x, right? So we can convert this into an ODE when the learning rate is very small, right? We're making one small update at a time. So that's going to be a differential equation. That's easier for us to analyze. And then you see here, this ODE is actually very simple, right? It's just going to be a linear ODE. So this means that we can analyze the spectral properties for this ODE. And that can give us some insights about the network architecture and about the data when training a neural network.